Okay, so this video, I'm going to talk about covalent bonding and bond polarity and electronegativity and a little bit about dipole moments. So we know that ionic bonding is the transfer of electrons between metal and nonmetals. They don't physically share the electrons, they share their charges and they form that electrostatic interaction between the positive and the negative. In covalent bonding, there's actually sharing of electrons happening. And that sharing occurs between two nonmetals. So when we're talking about covalent bonding, I'm talking about two elements off of the right side of the periodic table. So when we refer to covalent bonding, when we talk about these things, these are our molecular compounds that we're referring to, okay? And why are they sharing? The same reason why in ionic bonding metals are losing and nonmetals are gaining, it's to achieve that octet rule. So if something doesn't have 8 electrons, it's willing to share its electrons with another nonmetal in order to get that 8, okay? So how do we do this with covalent bonds? We use these things called the Lewis dot structures, and then that shows us how they're actually bonding. And we'll do a review on how to draw these Lewis structures, but for now, let's just talk about, okay, well, if they're sharing electrons, they're going to have bonds with each other. So how am I going to tell? If it's a single bond, that means they're sharing only 2 electrons. A double bond indicates they're sharing 4 electrons. And then a triple bond indicates that they're sharing 6 electrons. Okay, so that's just sort of the intro to covalent bonding. So let's talk about what is bond polarity, because we'll notice in ionic, we have a full positive and a full negative charge happening because there is a complete transfer of electrons. Well, in covalent bonding, there is not a complete transfer of electrons, they're sharing. So we have to kind of talk about, well, if they're sharing, does one element maybe want electrons more than the other element? And sort of how do we talk about that if that tends to be the case? Okay, so bond polarity is actually the equal or unequal sharing of electrons. Okay, and we can kind of talk about this in terms of like a game of tug of war, right? You're either going to have people that are super strong pulling to one side that are going to want that win more, or you're going to have people of like the same sort of physical build, and maybe the knot doesn't move anywhere because nobody's stronger than anybody else. So in reference to that, we can refer to it as nonpolar or polar. So when we're talking about nonpolar, this is equal sharing of electrons, where when something's polar, this is going to be our unequal sharing of electrons. Okay, and that kind of makes sense because when you think of polar or poles, you think of like positive and a negative, and that's exactly what's happening with a polar bond. So in order to identify whether a bond is going to be polar or nonpolar, we have to talk about this in terms of electronegativity. And electronegativity, basically, you can think of it just basically of who wants the electrons more. Okay, but ultimately, it's the want of electrons. So we identify the want of the electron for each element based off of just a number. The highest number is fluorine. So fluorine wants the electrons the most. So it has a 4.0 electronegativity. And then everything else on the periodic table is less than 4.0. And the trend is, as you go down a group, the electronegativity decreases. Where you go across a row, the electronegativity increases. And that makes sense, right? It decreases because the atom's getting larger, and it increases across a row because you're gaining more protons as you go across the row. So let's kind of look at what this looks like. In your notebook, you probably have a little bit better of an image than I do here. But in a nonpolar bond, you'll notice that this is between chlorine and chlorine. They both have an electronegativity of 3.0. So neither of them want the electrons more than each other. So they are just fine and dandy, just sort of like sitting there, not playing that game of tug of war. They're like, I won't move the knot if you don't move the knot type thing. So that's a non-polar situation. So with that being said, this compound isn't going to have this thing called a dipole moment. And a dipole moment means that there's a charge on one side of the atom or the other. There's no charge on this atom at all. It is completely neutral, zero, no charge, okay? Where if I look down here at my polar bond, I'll notice that I have hydrogen and chlorine here. Hydrogen has an electronegativity of 2.1, where chlorine has an electronegativity of 3.0. So that indicates that chlorine actually in the game of tug of war wants the electrons more to its side because it has more protons, okay? So we actually then introduce this thing called the dipole moment. So there is a dipole moment towards chlorine because it wants the electrons more. So you'll notice that when you draw a dipole moment, the arrow goes towards the element that wants the electrons more, where the positive end of the arrow is where you're going to have the element that's sort of just holding on to the rope in the game of tug of war, trying not to let go. So what we can start to say is, unlike in our ionic compounds where we just wrote a positive and a negative, you'll notice that we also have this guy here, which is the lowercase delta, which means partial. Because again, we can't say that it has a fully positive charge or a fully negative charge because it doesn't, right? Because they're sharing. So we then have to say that this compound has a partially positive end of the compound and a partially negative end of the compound. And because we have two partially charged sides, we have to say that it has a dipole moment, and that dipole moment goes towards chlorine because it's the negative side of the compound. Okay, and that's it for that. Thank you.